Right. So folks, welcome to the very last Monday of differential equations. Congratulations on making it so far. But today we're going to cover 7.3, which is called Operational Properties, Part 1. We will not be getting to 7.4, and that is okay. We'll probably just finish up 7.3. That'll be the last section on exam 3, not 4, 3. And then we'll go over section 7.6 a little bit this week, but it will not be on the exam this week. All right, so the exam, that topic list has been posted. If you haven't had a chance to check that out yet, please go ahead and do so you have a good idea on how to prepare for Thursday's exam. Okay. All right, so let's take a look at what we know. So what we know so far in chapter 7 is we've taken a look at, why is this not working? Hold on. We've taken a look at the formal definition of the Laplace transform, and that was in section 7.1. And so if for some reason on homework number 7, that was not a question you got correct, I would just make sure to take a look at the homework 7 solutions for number 1 if you're not sure about the formal definition. We've also spent a lot of our time really looking at how we use the table of the Laplace transform and primarily learning how to look at that in both directions. Okay, and so that would be an important piece to consider for Thursday's exam. And the last thing that we've really focused a lot on is sort of this supporting algebra piece of partial fraction decomposition. And so I just really want to make sure to emphasize that I do need you to show your work around this part. So whether you set up a matrix or whatnot, I do need to see some sort of this is how I got these numbers. Okay, so make sure to show your thinking around this process. Okay. All right, so that's really where we've been in chapter 7 so far. And so today what we're going to take a look at is more shortcuts, all right, more shortcuts to this formal definition. And so you can think about this like when we learned about derivatives for well, not us, but when you learned about derivatives for the very first time, and there was that formal definition, and then you start to learn all these rules like product rule and quotient rule, and that day maybe sort of blew your mind in Calc 1, but then you started to learn more and more rules. You learned about chain rule and implicit differentiation and so many other sort of shortcuts to take a derivative. And so this is sort of the parallel in 7.3. Now we're sort of adding more and more shortcuts. All right. So that might be just a perspective thing. If you're like, oh, all of these questions are so long, just remember they could be way longer. All right, they could be way longer. Maybe that'll help sort of frame where we need to channel that energy in this last week of class. And so this section is really all about translations. And so we're going to take a look at translations on the S-axis today. And if we have time, we'll start to take a look at translations on the T-axis as well. And so let's start by considering this particular function, e to the at f of t. And what we want to think about is taking the Laplace transform of that particular function, okay? And so if we start by having some technical difficulties. So if we start, we're going to say the Laplace transform of e to the at f of t, right? And so when we think about the Laplace transform, we really want to think about the idea of, let's bring it back to that formal definition, okay? And so if we think about that formal definition, we'll recall that it is an improper integral, bottom bound is 0, going all the way to infinity, of e to the negative st times whatever function we have here. And in particular, we're going to use this one right here, e to the at f of t. Right? And if we think about how we can actually simplify this, one thing we might notice is we have two terms with an e in the base, and that means the bases are the same, so we can actually think about combining our exponents here. And when we think about combining these exponents, we could rewrite this as the integral from 0 to infinity of e to the, I'm going to go ahead and write this as negative s plus a. All right, so negative s plus a times the quantity t. So I factored out that t times f of t dt. All right. And we're going to keep rewriting this little piece here in a few sort of clever ways. Okay. And here's what I mean by clever. If we think back to the formal definition, we know in the formal definition that there is a negative st. All right. And so what we're going to do is we're going to go ahead and take this sort of clump in front of the t, and we're going to factor out a negative sign. And let's see what we get. Integral from 0 to infinity of e to the negative. And if I factor out a negative sign, I'll get s minus a times the t. Okay, so all we've done is factor out that negative sign. And we still have our f of t dt. Now, why would we bother rewriting it? Oh, hold on one second. Oh, there we go. Okay. So why would we bother rewriting it? If we sort of revisit that formal definition real quick. All right, and when I say formal definition, I mean we're going to look at the structure of the formal definition, not that we're going to reprove it or anything like that, okay? But the formal definition said that if we take the Laplace transform of some function, that was the equivalent of the integral from 0 to infinity of e to the negative st times that function. And ultimately, we found that this is going to be equal to uppercase f of s. That's how we defined it, okay? And so what we're trying to do here is find a little bit of structure that is parallel between the two. And so we might notice that there is a dt in both the formal definition and the version we have here, okay? We have an f of t, which we have in both. We have the integral from 0 to infinity, which happens in both. And the one piece that is slightly different is in this case, we have e to the negative st, whereas in this case, we have e to the negative s minus a t, right? So in particular, the part that is different is in the original, we had an s, and in the new version that we have, what we might say is a translation. We're moving something in a specific direction. Now we have this s minus a. And so what that allows us to do is say, hey, this structure is so similar to this formal definition, okay, that it turns out the only thing that's going to be different about our answer is we're not going to have uppercase f of s, but we're going to have uppercase f of s minus a. All right. All of that is to say, when we have the Laplace transform that we've already defined. And we have some real number. Okay, so we're not considering imaginary numbers. We're shifting along this real axis. If we have something in the form of this, the Laplace transform of e to the at f of t, then we can say that is equivalent to uppercase f of s minus a. Okay, and this is so important that we call this the first translation theorem. So let's go ahead and, I don't know why there's a little bit of a lag right now. Let's go ahead and practice a few of these, okay? So it turns out that when we are looking at these, all of this, the translations we're going to talk about today actually help us move through a question a little bit more smoothly, okay? And so we're going to use this first translation theorem to evaluate the Laplace transform of each of these following functions, okay? And so let's begin. We've got, our question is saying, let's find the Laplace transform of e to the f 5t times t cubed, okay? And so we can see in this case that this is very similar to what we saw in this first translation theorem, right? In particular, we have this e to the 5t, which is like our e to the at, right? And so here's what we're going to do. We're going to find the Laplace transform of the t cubed part. All right, so if we're to think about this in steps, we're going to take the Laplace transform of the t cubed. And so let me go ahead and pull up that table again. And I'll drop that link in the chat in case you don't have that pulled up already. Where did it go? All right, so let's open up that table. Again, there are other tables out there. I think it's just convenient for us to be able to say, let's look at this line and everybody's looking at the same table, okay? So let's go ahead and use our table to find the Laplace transform of t cubed, all right? So take a moment, find the line on the table that you need to find that Laplace transform. Go ahead and plug in the numbers. And when you get that value or the output function rather, go ahead and put that in the chat. All right, looks like we got a 2t cubed. All right, so I think you were using line number 3 in the table, right? Line number 3 to find that Laplace transform. And so if we're using line number 3, maybe it would be important to identify what our n is in this case. Yeah, and I think our n in this case, because we're going in the forward direction, n is actually the number that's there, right? And so we have to think about using that value, not subtracting 1, like we go back in the other direction. So we're going to plug n in everywhere we see an n, or plug in 3 everywhere we see an n in line number 3. Okay, so that's going to give us, whoops, 3 factorial over s to the 3 plus 1, okay, which does give us 3 factorial over s to the 4th, all right? And so all we've done so far is just say, let's find the Laplace transform of the f of t part, right? The t cubed part, not the exponential part, but just the t cubed part. And then what we're going to do using this first translation theorem is we're going to shift that so that everywhere we see an s, we're going to replace that with an s minus 5. It's almost like we get to do the problem in 2 steps instead of saying, let me go to the table and find what I need to find, okay? So for step number 2, we're going to apply the s minus a translation. Okay. And so all we mean by that is everywhere we see an s, we're going to replace that with s minus a. And so it would be really important for us to also know what our a is in this point. So a equals 5 because we have e to the 5t. Okay. So all that means is that our Laplace transform of this shift along the s-axis is going to be 3 factorial. But instead of writing s to the 4th, we're going to write s minus 5 to the 4th. Right? And if you look at this table, you'll notice that we do not have something that looks like e to the at t cubed until go all the way down to line number 23. Okay, so make sure you can find line 23 on here. That's where that comes from. Okay, so this first translation theorem is actually how we're able to add line number 23 to our table. Okay. So let's take a stab at example number 2. Okay, I'd like us to sort of break this up into 2 different steps where we find our Laplace transform of f of t. Okay, so this first part, I think that's a really good place to practice reading the table, making sure we're plugging in things accurately, right? And then let's go ahead and apply that first translation theorem. Either way, we can check our answer because the output should be what line 23 gives us. Okay. All right, so let's go ahead. Dan, it looks like you are ahead of me, which is awesome. Let me go ahead and write that down. We're going to go ahead and find our Laplace of f of t. And in this case, that gives us the Laplace transform of cosine 4t. All right, so I love that you've given a formula in there. Let's make sure that we've got the first part though. Okay, so if we were to sort of remove the a, right, we're only looking to read the table for a cosine of 4t. That's going to bring us up to line 8. We're going to have s over s squared plus 4 squared, right? So we break this down step by step. We look at that table, we're going to get s over s squared plus 4 squared. Now let's apply the shift. All right, now let's apply the shift. So we apply our s minus a translation. And so in this case, what can we identify as our a in question number 2?
A equals 4.
Our A does not actually equal 4 in this case. If we're thinking about the actual translation, that comes from the first part, the part with the E. Yeah, Dan, you're right. It's going to be a 2. But let's be a little bit more specific now. We want to note that we have a negative 2 here. Okay, so negative 2 for this translation. That means that everywhere we see an S, we're now going to replace it with S minus negative 2. Okay. So that means that our Laplace transform of e to the negative 2t cosine of 4t is going to equal S plus 2, right? Because that is our S minus negative 2. And then S plus 2 squared plus, and you could write 4 squared or you could write 16 squared. Okay. I think what makes this sort of tricky is that we have 2 different levels of A's. So we need to be thoughtful about which one is which. And I think the table actually makes that a little bit more clear here. Right? If we look at line number 23, that one works for example 1, but we would have to use a different line for example number 2, right? And in particular, we're looking at line number 20 for example number 2. All right, but this is a nice way to make sure if you can use line number 20 to get this answer, then you know, okay, if I break it down into 2 steps, I should still get that same answer. Okay. All right, let's pause real quick right here. We've got example 1 and example 2 up on the screen. Are there any questions so far about where things are coming from or where things went?
I just have a question about example number 1. Is there a reason that you leave the 3 factorial instead of just putting 6, or is that for like a further step down the line, or?
That's a great question. I think that a lot of times when we use factorial, like there's no reason we can't say 6, but we might end up like in a different problem, and not necessarily in this class, but I think just sort of in higher level math in general, where you might have something like 6 factorial times 3 factorial over 4 factorial. And if you were to multiply them out and then reduce your fraction, that would take a lot longer. But one thing we could do from here is we could say that 4 factorial will reduce with much of the 6 factorial. We'll only end up with 6 times 5 left. And so some people might just choose to leave it in the factorial form because it'll be easier to reduce later on if you need to. But also if you have like, I don't know, 7 factorial, it might just end up being a really big number and maybe you just don't want to multiply it all out. So I think that's more of a like, not laziness issue, but you know, there's nothing wrong with turning 3 factorial into 6. Like that wouldn't, you wouldn't lose any points for that. All right. Any other questions so far on example 1 and 2? Okay. Now, before we move on to the next 2 examples, I do want to put maybe up at the top right here, some notation that you might see if we're sort of moving in this direction, okay? And we might see that the Laplace transform of e to the at f of t, all right, because we recognize that we're going to have a translation here, sometimes we write this as find the Laplace transform of f of t. And then we're going to say, but everywhere we see an s, we're going to replace that with s minus a. Okay. So this right here, if you read through your textbook, they'll give you that notation. All that means is what we did in step 1, find that Laplace transform of f of t. Then this second part, s goes to s minus a, is the apply the translation part, okay? So that's how we move in one direction. We're finding the Laplace transform. But as we know, when we solve differential equations with Laplace transforms, it's really important that we know how to go in the other direction as well. And so we're actually going to take a look at how we go backwards here. Okay.
Professor, excuse me, just really quick before we move on, back to example number 2. If we use rule number 8, so with that cosine 4, I was thinking the 4 is a squared. So then if a squared is 4, then I was thinking, that's why I was thinking it was 2. So is that?
Right. So yeah, let's go ahead and look at line number 2 real quick, okay? Or sorry, 8. So line number 8, if we go to the table, it says that if we have cosine of AT, that when we apply the Laplace transform, we end up with S over S squared plus A squared, right? So you tell me, what's your A value?
Yeah, okay, I see.
Yeah, I know. I think that's what makes it so tricky, is that like we go in both directions. And so sometimes we're like, oh, we squared it already, so now we square root it. But
Yeah,
that makes total sense where you would get that from. Yeah. Okay.
All right, thank you.
Of course. All right. So let's think about how we might go in the opposite direction here. Okay. And so maybe we start off by sort of writing what that inverse Laplace transform looks like for us. All right. So if we take the inverse Laplace and we have f of s minus a. So we notice that we might have a shift. All right. And we think about this shift. What is the shift that we think we see in example number 3? So if we look at example number 3, how do we think that this is being translated? Yeah, exactly, right? I look at the numerator and I'm like, I don't really see like an s minus a, but when I look at the denominator, I have an s minus 3. That's a good clue that I'm really shifting by 3, or that my sort of second step in the other problems we just saw move things to the right 3, okay? So when we see this kind of structure, what we're saying is that we can work backwards, that we can take the inverse Laplace of just f of s, and then, my bracket's in the wrong place. And then we're going to say where we have this shift, and that's going to be equal to e to the at times f of t. All right. It is the equivalent statement of what we just wrote above, except now we're saying we're going to go in the other direction. All right. So let's see how this plays out. So let's go ahead, and if we're finding the inverse Laplace of this, 2s plus 5 over s minus 3 squared. Right. Let's see if we can break this up into things where we can actually read from the table, okay? And we might even want to remind ourselves that we're reading from the right-hand column back to the left-hand column in our table. And so I think we know by now that when we see something like this, we're going to need to use partial fractions, right? And whether we choose to set up a system of equations or whether we choose to use a matrix, we should have some sort of setup structure so that we can tell like where these numbers are coming from, okay? And so we might even say this is going to be equal to the inverse Laplace of, how many fractions are we going to have when we set this up into partial fractions?
Two.
Yeah, we're going to have 2. First denominator.
S minus 3.
Mm-hmm. And that one will have a constant at the top, right? We'll have a over s minus 3 plus, what's the second denominator?
S minus 3 squared.
Perfect. All right, what's that numerator?
Is that BS plus C?
Ah, okay.
No?
So
Oh,
BS plus C, yes or no? What do we think? All right, so I do want to, where would be a good place to write this down? I do want to write this out because I think that it was an issue for some of us on that last homework, right? So I know it doesn't go in this section, but let's just get it in the notes somewhere. For partial fraction decomposition. If you have a linear factor on the top, you're going to have a constant, right? And so we've seen that a lot where we have like the first one we had a over s minus 3. But when we have, I don't want to just write quadratic. I want to take the time to write out this extra word, irreducible quadratic. Okay. If you have an irreducible quadratic, then you have a linear factor on the bottom, okay? However, if you have, and we replace this irreducible with a reducible quadratic. Reducible quadratic means that you actually have linear factors down there. So if you have linear factors down there, you'll need a constant at the top, okay? So the difference there, if you have an irreducible quadratic, then you want your BS plus C or your linear factor. However, if that is a reducible quadratic, meaning you can make it a product of linear factors, then you have a constant on the top, okay? And so if we bring this back down to example number 3, all right, and we take a look at this factor, s minus 3 squared, yeah, that's a quadratic, but is it reducible? And it sure is. It reduces to s minus 3 times s minus 3. And since it's reducible, we actually want to say we want a constant on the top, okay? I know that's weird. It is a place that trips up students of all levels, right? It doesn't matter if you're in pre-calc seeing partial fractions for the first time, or you're in differential equations on the other end, like so ready to move on to the next phase of your mathematical career. It's definitely a place where we just need to be really careful about our setup, okay? If you add other letters, you'll find that one of them will be 0, and that you'll have sort of created more work for yourself in achieving that answer, okay? So if you want to go ahead and do more work, that's absolutely fine. But if you already know one of them is going to be 0 all the time, maybe we save ourselves a little bit of that work, okay? All right, so let's do a quick partial fraction decomposition here. We're going to have 2s plus 5 equals a times s minus 3 plus b times 1, right? The only thing I need to do to make the denominators the same is multiply that first fraction by s minus 3. If we were to go ahead and expand this, we would get 2s plus 5 equals as minus 3a plus b, right? From here, we can set up a quick system of equations, and we'll see that 2s equals as, or a equals 2, right? And that's just by grouping, let's not use pink, this one and this one to give us this equation. And then we could group all the constants. So 5 equals negative 3 plus 3a plus b, right? So 5 equals negative 3a plus b. Since I already know a, I'm going to go ahead and substitute that in. So I'm going to end up with b equals 11. Okay. So we're able to now write our inverse Laplace as 2 separate fractions that we can now use our table for, okay? And so what we really have here is the inverse Laplace of 2 over s minus 3 plus 11 over s minus 3 squared. All right. The first one, we can certainly say, let's just go straight to the table, right? We're going to have 2 times the inverse Laplace of 1 over s minus 3 plus 11 times the inverse Laplace of 1 over s minus 3 squared. All right. From the table, I think this first one should be, where is it? Line number 2, right? Line number 2 in our table. And we are going in the opposite direction this time, right? We're reading from the right column to the left column. And so our output will be 2e to the 3t. What line on the table tells us about that second term? right, we have so many lines on this table. Which one tells us about the second term?
So 23.
Let's see, line 23. We could get pretty close to that, right? Our n in this case would be, what would our n be in this case?
2.
So let's write that down, line number 23. And we're even going to say that n equals 2. All right. So if n equals 2 over here, then when we sort of go backwards on line number 23, we're going to have to compensate for our numerator, right? Our numerator right now is a 1. But according to the table, it would have to be a 2 in order for us to use that line. Thoughts? Is that logic correct?
So n just equals 1 then, is that right?
Yeah. Okay.
Okay.
So let's actually write that out, right? I think this is the part where, like, if we're all in the classroom and I had the table projected on the screen and then we're like writing on the whiteboard as well, it's easier to see side by side. But according to the table, it says that if you see n factorial over s minus a to the n plus 1, then the inverse Laplace of that is t to the n e to the at, right? That's what the table tells us. And so we want to make sure we note here that this power is n plus 1. So that means our power, if our power is 2, our n value is actually 1. Because in the strangest way here, we are revisiting the idea that 1 plus 1 equals 2, right? So we want to make sure that we have the right n so that when we look down here, we'll plug in the correct number, right? And that also means that we have a little bit less work to do, because if n is 1, 1 factorial is 1. So I don't have to worry about changing that numerator to match my equation, right? It's already matched. So I know my n is 1. I might even want to write out my a is 3, right? And then I can put both of those into the left-hand side of that particular row. So we'll get t to the first power times e to the 3t. And we don't want to forget that we had that 11 as our constant. So I'm going to go ahead and bump this out a little bit so I can add that 11 in the front. Now, this is line 23 on our table, right? But how does this apply to this idea of the translation or this shift in the other direction that we were thinking about? Well, we could have approached this second part in a slightly different way, okay? So we could have done this instead. We could have said, we're going to have 11 times the inverse Laplace of 1 over, let's unshift it for a moment, s squared. And then we'll say, we'll replace that s with the s minus a, right? And 1 over s squared, well, that corresponds to line number 3 in our table. And we would get 11 times that t, but then we are shifting that, right? So t to the first power. Now we're shifting that s minus 3. And when we apply that, that's where that shift comes in. Okay, we can say shift, we can say translation, but thinking about where these other lines in the table come from, they just took 2 steps and they said, hey, this is a really great way. This is a shortcut that I can do. And it's so common that let's just go ahead and document it in the table. Okay. All right, before we take a look at an initial value problem, all right, are there any questions about example number 3? All right, so let's go ahead and take a look at example number 4. All right, so we're going to take a look at the goal of this, right? Why are we using all of these? Why are we learning how to use the table? We're using the, or learning how to use the table so that we can solve an initial value problem, all right? And so we have a second order differential equation here. It is non-homogeneous. And I know it's non-homogeneous because it does not equal 0, but rather we have t squared times e to the 3t. And so we can kind of see here that we have that shift, right? E to the 3t times t squared. So I've got my shift of 3, just like some of the earlier questions that we saw. Because we have a second order, right? The highest derivative is a second derivative, so second order. We have a pair of initial values or initial, initial values. So we've got y of 0 equals 2, we've got y prime of 0 equals 17. We're going to apply those sort of in that second step as we transform things, right? So let's go ahead and take a look at our first step. All right. So the first thing we are going to do is we are going to go from calculus to algebra, or another way to say that is we are going to apply the Laplace transform. All right. So dig back into your notes from last week. We had certain things that we needed to plug in for y double prime, y prime, and y, right? Let's find out what those are. We're going to plug those in to the left-hand side of this differential equation. We're going to turn that into an algebra problem. And then we have to use our table to find the Laplace transform of the right-hand side. Okay, so we want to make sure that we do both sides of the equation here. All right, so I'll give you a moment to find those values and write them in, what your y double prime is, what your y prime is, what your y is. And one thing that I think most of us were really good about, keeping in mind that the Laplace transform is an uppercase y of s, whereas if we have our lowercase y, that's really refers to y of t, right? Lowercase y is like our lowercase f of t, whereas the uppercase stands for the Laplace transform part, okay? So again, most of you were pretty good about that on the homework, but there might be 1 or 2 of you that want to be a little bit more cautious on that, okay? All right, I forgot what colors we used last week, but new week, new colors. I think these might have been it, but I cannot remember. All right, so if we go ahead and substitute that in, we should end up with, and I'll put these in brackets, we should end up with s squared uppercase y of s minus sy of 0 minus y prime of 0. All of that corresponds to the y double prime that we have. Minus 6. All right, let's plug in what we have for y prime. S uppercase y of s minus y of 0. This corresponds to that y prime plus 9. And I'm going to put brackets here, even though there's only one term here, so I technically don't have to. But now I've plugged in everything I need on that left-hand side, right? My y double prime, my y prime, and my y. And now let's think about the Laplace transform for the right-hand side. And so this one should correspond to what we already know in line 23, right? So what is our, if we use line 23, we need to identify our n as well as our a, okay? So go ahead and tell me what those, what our n is and what our a is in this particular case. All right, according to line 23, our n is 2, our a is 3. I would agree with that. Okay. And if we think about what we're plugging it into, we want to have n factorial over s minus a to the n plus 1. Okay. And so if we go ahead and plug that in, we're going to end up with 2 over s minus 3 to the third power, right? 2 over s minus 3 to the third power. And if you find this strategy helpful, like write out your n, write out your a and the formula, and then plug it in, by all means do that, right? Do what you need to make sure that you're not making small mistakes that cost you like the accuracy of the problem, okay? But before we write that down, let's go ahead and unpack that left-hand side, right? So let's figure out how we might want to clump our terms, all right? And again, if you find yourself making mistakes here, I would take the time to just distribute all the things that you need to distribute, right? Making sure you don't lose any coefficients. And so if we did that, we would end up with s squared y of s minus s. And now we can sort of start to put in those initial conditions, right? Instead of y of 0, I'm going to go ahead and put a 2 there. And then instead of y prime of 0, I'm going to put a 17. Minus 6s uppercase y of s plus 6 times 2 plus 9 uppercase y of s is going to equal, now let's go ahead and write down our 2 over s minus 3 cubed. A few places where I see folks potentially going wrong. The number one spot, that -6 times a -2, making it a positive 12, right? That's probably the biggest place that is the easiest to make the mistake, right? But once we've applied those initial conditions, we can now collect our y of s's, right? So we're going to go ahead and say this term has a y of s, this term has a y of s, this one has a y of s. And so we have y of s squared minus 6s plus 9. Okay. Let's see, minus 2s. So that's this minus s times 2. And then I'm going to go ahead and combine negative 17 plus 12, which will give me minus 5. All of that equals 2 over s minus 3 cubed. Now I'm going to go ahead and add the 2s and the 5 to the other side. And at the same time, I'm going to factor s squared minus 6s plus 9. Okay, so I'm going to get y of s times s minus 3 squared equals 2s plus 5 plus 2 over s minus 3 cubed. All right, last step to solve for my y of s here, we're going to go ahead and divide both sides by that s minus 3 squared, right? So we're going to end up with y of s equals 2s plus 5 over s minus 3 squared plus 2 over, I know this is kind of weird looking, but we actually have, since we already have 3 of these here, and we're sort of introducing another 2, s minus 3 to the 5th. All right. So we've done our solution, right? We've applied our Laplace transform. We found our y of s, except now we need to unpack it. We need to go back into our lowercase y of t situation, all right? So clearly I did not space things very well. Here's what we're going to do. We're going to add another page. I'm going to copy this problem to the other page. Whoops. And leave that right here. And we're just going to pretend like we don't have this line right here. Okay. All right, so we've applied the Laplace transforms and the initial conditions. Well, we now have to figure out how to undo this, right? How do we get back into the world of t? So let's put that part down here. Step number 2, we have to apply our inverse Laplace of our y of s to find our lowercase y of t. Okay. And so if we take a moment to do that, we have the inverse Laplace of y of s. That's going to give us our y of t. Okay. But we have to take the inverse Laplace of each of these terms here. I'm going to go ahead and say this piece right here. Well, didn't we see that before? This was actually the same thing as we had in the previous example, right? 2s plus 5 over s minus 3 squared. if we go back in our notes to s plus 5, s minus 3 squared. Okay, so if we didn't have this, we would have to now insert all of the work that we did here to help us find that particular answer, right? Luckily, we can just grab this solution and kind of move on with the question just because we've already done that work. Okay, but in a regular problem where you haven't already done that inverse Laplace, you would have to go through this process. Okay, so I'm going to go ahead and just grab this answer right here, the 2e to the 3t plus 11te to the 3t. That's going to be the inverse Laplace of the first term that we have. And we'll leave ourselves a little note so we aren't thinking, where did this magical answer come from? And we'll say C, problem number 3. Okay. Whoops, but we do need to find the inverse Laplace of the second term. So let's go ahead and bring a 2 out to the front, inverse Laplace of 1 over s minus 3 to the 5th. Right. All right. So while I go ahead and write down what we had from number 3 for the first two, I would like you to go ahead and start looking at the table and think about what you need to maybe manipulate to help find the inverse Laplace of that second fraction. Okay. Right, and in particular, we might want to think about what line on the table we're going to need to use. And how that might impact the coefficients that we have. Okay. All right, so what line in the table are we thinking for this second inverse Laplace?
I think it's going to be number 23 again.
Yeah. All right, so line number 23, what do we have for our values? I think we need an N and an A, yeah?
So N will be 4, A would be 3.
Good, good, good. All right, so this is sort of the part where we have to do a little bit of thinking, right? It would be so easy to say, oh, here's my power, that's going to be my N. But when we look at that table, we realize that that power is really N plus 1, right? So our N here is 4. Now, what that means is we need to think about how we get a 4 factorial in this numerator, right? And so we're going to do our fancy way of multiplying by 1. And we can go ahead and actually say 2 inverse Laplace of 4 factorial over 4 factorial, right? That's just 1. I didn't change anything, times 1 over s minus 3 to the 4 plus 1, right? This numerator 4 factorial is going to stay on the inside so we can use our table, but this denominator 4 factorial, we can go ahead and pull out and put underneath that coefficient of 2 that we already have in the front. So we get 2e to the 3t plus 11e to the 3t, whoops, 11t e to the 3t plus 2 over 4 factorial. And then when we apply that transform in the opposite direction, we'll end up with t to the 4th power and then e to the 3t. All right. So let's go ahead and get this all on one page for us right here. All right, so we've walked through an initial value problem. It's not significantly different from the kind of problems we were doing last week, except we don't want to panic when we see something a little bit more complicated on the right-hand side. Rather, we really want to think, okay, this just means we need to dig a little bit deeper, find some of those more, those lines towards the bottom of the table that we hadn't really explored last week, but also think about where this came from, okay? And so we have one more question left here, okay? So we have this question, example number 5. And I think what I'm gonna do is say, let's take that, but since we don't have a homework this week, I'd like you to work through this problem today, okay? It's not for a grade, but to think about rather like, how are we gonna prepare for this exam on Thursday, okay? So go ahead and work through example number 5. And tomorrow when we start class, we'll go ahead and work through that together just to make sure that your steps sort of match what you know, everyone else's steps are. And that way we can have a chance to really practice reading that table and being aware of where we as individuals tend to make mistakes, right? Because that's going to be a little bit different for everyone. And so we'll start tomorrow by going over example number 5, and then we will move on to translation on the t-axis, where we're actually going to take a look at that heavy side function. Okay, now the heavy side function is something that I think that word should be familiar because we had that for our very last discussion, right? Thinking about just sort of looking ahead, what are these terms, what are these vocabulary pieces that are coming up, and how might that help us have more access to the content in class, okay? So tomorrow we'll take a look at the translation on the t-axis, and again, it'll be sort of using some of the lower rows on this table to help us figure out how to go back and forth between a Laplace and an inverse Laplace, but more specifically, how do we use that to solve a differential equation, okay? And so with that, I give you a little bit of gift of time for you to maybe work a little bit on your own, again, just for that self-awareness, like where am I as an individual? What do I need to do before Thursday to make sure I finish this course in a way that makes me feel successful, okay? So I'm gonna go ahead and stop the recording here.